Okay guys, I'm going to now record a video to help you out with lab number 4, which is this lab regarding matter and phase changes. So the first thing I want to talk about is the section where they ask you to identify the different phase changes. So what they're asking you to do is to think about the type of energy that's taking place, the type of energy changes that are taking place. So they let you know that the total energy, just like we talked about before with the roller coaster, is just the kinetic energy of the molecules. So this is of the molecules. So whether you have solid, liquid, or gas, they do move around a little bit. And also the potential energy of the molecules. So this is referring to the attractions between the molecules. So to clarify here, I mean attractions between, for example, two water molecules. I'm not referring to the bonds between the individual atoms, so this is between molecules, not atoms. And these are the, I'll write it over here, intermolecular forces. So these intermolecular forces, like I said, these attractions are responsible for the phase changes. So phase changes occur when the attractions are weakened. So remember we talked about the fact that the energy between particles is, lowest for the gas, and then it's a little bit stronger for the liquid, and it's strongest of all for the solid. So basically, what you want to look for when you're looking for a phase change is changes between the attractions between the particles, between the molecules. And let me get a little bit more specific. So they talk about a few different types of phase changes that you might not be familiar with. So one you probably know is condensation. This happens, for example, when you leave a glass of water sitting on the table and it's hot outside, the gas from the atmosphere condenses onto the outside of the glass. So this is when a gas goes to a liquid. And this is basically what you're going to be doing later during the distillation part of the lab. You're going to be evaporating some liquid and then condensing it away to separate it. I'll talk a bit about distillation in a second. So yes, condensation is when we're going from gas going to a liquid. Another one they talk about is sublimation. So this is one you don't see often at like ambient conditions, but basically this is when a solid goes straight to a gas. And furthermore, there's deposition, which is the opposite. So a deposition is when a gas goes to a solid. They're definitely going to ask you about both of these things in lab number 4, so keep your eyes peeled for that. So let's talk next. The next topic they ask you about that you might not be that familiar with, we definitely didn't cover it in lecture, are these heating curves. So let me write, can you see that? Yes, heating curves. So the point of these things is basically to track the temperature changes as heat is added to a system. So it looks something like this. On this axis we have heat added. And on this axis we have the temperature of the system. So I'm going to show you the example for water, which is what they're going to ask you about in the simulation. So basically what happens is we have our solid starting off at room temperature, and it creates a curve like this. As it reaches a certain point, this solid begins to melt, so all of the heat being added just goes into breaking apart the forces between the molecules in the solid. So basically what's happening is that there's heat being added to the system, but the temperature is remaining constant. So at a constant temperature, all of this heat is being used to break apart the intermolecular interactions. Once that happens and we enter our liquid phase, which looks something like this, we go through another phase change once again. So the liquid's going to become a gas, and it's going to take some some energy to do that. So yeah, once again, this is our solid phase. So we'll put an S here. This is our liquid. This is our gas. And these areas with the stars are the phase changes. So I'll say this one is going from solid to liquid. So we know that this is melting. And then the double star is going from liquid to gas. So we know that this is evaporation. And once again, these phase changes are occurring at constant temperature. So the slope in these regions is 0. So that's another way to say it. So slope, which is the change in temperature over the change in heat, is equal to 0. Now you might have noticed that our phases have slopes. So once again, the slope is going to be equal to the change in temperature over the change in heat. That's just how you read the graph. And they're going to ask you some questions, kind of qualitative, about what this slope is referring to. So basically, if you have a higher slope, what that means is that you have a large delta T for a small delta Q. So if you add a little bit of energy, a little bit of heat, your temperature changes very rapidly. So what that means is that it takes less heat to change the temperature. And the opposite is true as well. So if you have a lower slope, let's say lower slope, that means you have a smaller change in temperature for a larger change in heat. So it's the exact opposite scenario. It's taking even more heat to change the temperature. So look out for that while you're doing the simulation, which phase is easier or harder to heat up. What else? The last thing they mentioned that I think we didn't talk about in class is this idea of latent heat. So let me write it here, latent heat. And this is just the heat involved in the phase changes. And if you can identify where the phase changes are on this graph, you should be able to identify the latent heat. So for example, the latent heat of this change going from the liquid to the gas is this quantity right here. So a certain amount of heat was added in order to do this. You could read it, if this graph had numerical labels, you would be able to figure out how much heat was added for this phase change to occur. So that's where the latent heat comes from. On this graph, there's two different latent heats that have special names. So the one at singular star here, for the melting, is this heat of fusion. And then for this double star, this is known as the heat of vaporization. And once again, by looking at this graph, you should be able to tell whether the heat of fusion or the heat of vaporization is bigger by the magnitude of, or the length basically of these flat lines. So the longer flat line has more heat for the phase change needed. I think that's pretty much all I need to tell you. Everything else you should be able to learn from the theory sections or from what we've done in lecture. So I hope this is useful, and feel free to try number 4 again, and good luck, and I'll see you on Monday.